Hello guys, I'm Eshan Tripathi, Physics faculty at IIT-JEE, and let us start today with the third lecture of work energy power. So we already have had discussion over what work is and what work energy theorem is. And in today's this lecture of ours, we're going to discuss the potential energy, what potential energy is. We have already learned what kinetic energy is, but now we need to go to potential energy. Then gravitational potential energy, we're going to understand what it is, one particular kind of potential energy. And then conservation of mechanical energy. That's what we're going to discuss in the end. So without wasting any time, let's just start with the first thing, which is potential energy. So if you're learning it in school, they would say potential energy is the energy that is stored or conserved in an object or a substance. Now, this could be due to different phenomena in different motions, you could say, or different configurations, you could say, in different cases. So, as it says, the stored energy is based on position, arrangement, or state of object. Now, what exactly does it mean? So, as we have shown an animation or this picture over here, what it shows is that when something is pulled back, it was kind of we put in efforts to pull it back. And when we release it, it moves with a lot of energy, right? Energy was what? Kinetic energy, speed, all those things we're talking about. So basically, when it's pulled back and released, it's getting faster. Earlier, when it was at rest, it had no energy, but now it has some energy. So basically, where is that energy coming from? So what we are saying over here is when we pulled it back, it's like we gave it some energy. We have stored some energy in the body. And that later on is getting converted into kinetic energy, as it says. So all these things we're going to discuss in details in a topic we're going to discuss later. But for now, the point is sometimes this energy can be stored inside it. That's the word we're using over. It can be stored in an object. So when we pulled it back, this energy got stored. This ball became energetic. So that is what the basic idea of potential energy is, what we are going over here. Now, as I said, this can be stored in different forms. One was like pulling it back, as you could see in this example again. We were pulling it back. So kind of gravity was pulling it down, isn't it? Imagine if gravity was not there. Would this thing even happen? Like, would energy be stored if gravity was not there? Imagine doing this in outer space, pulling a ball back. You release it. Nothing is going to happen. It will stay where it is. Gravity was important over here. But imagine this. The second case, first of all, let's see. If you pull an arrow backwards, so even if you do it in outer space, this energy will be stored now. If you release it, it is going to, even in outer space without any gravity, it would be going with some speed later. So the form in which potential energy is getting stored depends upon the force which is actually storing it. Like in the previous case, it was gravitation. Even in the case of hammer hitting a nail. So we are assuming like we are not hitting it like with full efforts, we are just kind of releasing it from a height. So yeah, gravity again is responsible for providing it this hammer some energy to be able to penetrate this nail into the ground. But in this case, this example of bow and arrow, it is not getting stored because of gravity. It is getting stored because of the stretchability of the, I should say, the string or this bow, right? So it depends upon the force. That is why there are different types of potential energies, which we are going to discuss also. But for now, the first one we're going to start with is gravitational potential energy. So we'll understand what gravitational potential energy is. As it clearly states over here, gravitational potential energy is energy stored in an object as a result of its vertical position or height. So, for example, like in this case also, which we mentioned earlier, this one, when we are pulling it back, it's kind of we are raising it higher. So when we raise it high, some energy is getting stored in it, as we discussed earlier. In this case example also, in the case of hammer, we were pulling it up. That is why when we release it, it moves down and gains some energy. It starts moving with some kinetic energy. So that is what we are saying over here. Because of its vertical height or position, the body is gaining some gravitational potential energy. Why gravitational? Because it's getting stored because of gravitational attraction of Earth only. No other reason is. So, in a very loose sense, like in layman's language, we can say, yeah, gravitational potential energy is energy stored because of height. But let's try to understand it from mathematical point of view, like in very much details. Then you would realize it is actually defined as work done by an external agent in quasi-statically displacing an object against gravitational force. What is this thing? Let's see what it is. Um, See what it says is, let us assume there is this ground and there is a man, and this man is going to pull and lift an object up. So there's a body of mass m, and he wants to lift it up. So finally, he lifts it to a height of, let's say, small h. The question is how much work? Why the question is how much work? Basically, why is energy getting stored? You already have got the feeling that some energy is getting stored in the object. But the question is, why is it getting stored? At what cost is it coming? Can you imagine? Can you like realize this? That it is coming because the man is putting efforts in lifting it up. Because man gave, man put in efforts. Man did some work. That effort only is going to give it some energy. That effort of the man is getting stored in the energy of the body. Getting this feeling. The question is, what is the amount of work that the man did? Now, that is what we are saying over here. It is the work done by an external agent. What is the external agent? The man in this case. The energies of the body of mass m. But we are saying the work is done by an external agent, which is man in this case. He is doing the work. Quasi statically. Now, what does quasi statically means? Quasi means false. False, or I can say, yeah, it's kind of a synonym of false. And statically means at rest. Now, quasi statically means falsely at rest. So, what it means is, now like these are very quadratic, like quasi static should be meaning moving, but it's not. It's like semi static, semi rest. See, what we mean by it is the body was at rest at the bottom. We are ensuring that this man is lifting the body up very, very slowly, very slowly. Like the body was at rest at the bottom, even when it has been risen from height h, it is still at rest. So quasi statically for us means almost at rest, very slowly. In brackets, I can write very slowly. So something is getting lifted up very slowly. That is like if something is lifted very slowly, whatever amount of work the external agent did, that is the gravitational potential energy stored. So in this case, what is the force acting on the body of mass m when the man is trying to lift it? That is, first of all, the weight of the body. M is the mass of the body, and acceleration due to gravity is g. So definitely mg force is acting downwards. The weight of the body is mg downwards, and that was acting throughout. Now, if I ask you, what should be the force that man should apply so that it gets lifted up very slowly? Very slowly means no gain in velocity. No gain in velocity means no acceleration. Almost in equilibrium, it should be moved up. I know you would say it's not possible. If the body does not gain velocity, how would it even move? I agree with that. But this velocity is there, but it's like 0.000000000000001 meters per second. So basically, what it means is, of course, it's a theoretical term that we are defining. We can assume it to be very small. We're not talking about its practical meaning. We are saying, like, we're not talking about practical feasibility. We are saying, if the man moved it up very slowly, how much effort would he do? What do you have to put in? So that's what we are saying. If the weight of the body is mg downwards, what must be the force that he must apply upwards so that the body gets lifted up very slowly, almost at equilibrium? You can imagine that this external force man is applying should almost be equal to mg only. Like he should apply almost equal amount of force. Yeah. So The question was, what is the work done by the external agent? Work done by this external agent or the man is going to be the dot product of the force that he applies with the displacement that happens of the block. What is the force that he applies? Mg. Direction upwards. He is applying F external equal to Mg upwards. And what is the displacement? Displacement is also H upwards only of the block. So cos of angle is zero. So that's Mgh. So basically, the work that the external man did, whose efforts are getting stored in the gravitational potential energy, is Mgh. So that is why we say that the work done that he has done, that has gone into the change in gravitational potential energy, Mgh. So basically, when this body has been lifted up through H, then the gravitational potential energy of the body has increased by mg. That is what we are saying. Getting this fact. For example, there is a body of mass m over here. It has been lifted up through a height h. So if I say at this position, let's use a different color. If I say at this position, the gravitational potential energy is 0 joules. So what will be the potential energy later on? It has increased by mgh. So we can say it's positive mgh. So if this was 0, this is mgh. And if I further raise it up to, let's say, another height of h naught, let's say, then again a further increase of mgh naught is going to be there. An increase of mgh naught, that means potential energy will be mgh plus mgh naught. So that is how potential will keep on increasing if somebody moves up, and will keep on decreasing as somebody moves down. That is what this theory is saying. Okay. So we have talked about this, and so let's move to a question on this thing. A basketball weighing 2.2 kg falls off a building to ground 50 meters below. Calculate the change in gravitational potential energy of the ball by the time it hits the bottom. So let's try this. There is this ground, and yeah, there is a body. Very simple question it is. There is a body of mass m. Mass is actually 2.2 kgs, and it drops off building to a ground 50 meters below. Basically, the height to which it has dropped is 50 meters. So, what is the change in gravitational potential energy of the ball by the time it hits the bottom? So, the change in gravitational potential energy, in this case, what they mean is the loss in gravitational potential energy is again mgh. Mass is 2.2. G, it's not mentioned. None of the values are multiple of 7. So, I think we can safely take it to be 10 into the change in height, that's 50. So whatever it is, that is going to be the answer. Okay, this much joules. So pretty simple question, nothing much to discuss in this. And then after this, let's see the next concept, which is actually going to use the gravitational potential energy. That is the concept of conservation of energy, or you can call it conservation of mechanical energy. What it says is that sum of all energies possessed by a body, all energy, sorry, sum of all energies possessed by a body, the sum of it remains same. Or in other words, one form of energy gets converted into another. Actually, we have already talked about the intuition of it. Whatever amount of effort he was putting in, that is getting converted into the gravitational potential energy. So we'll see some more examples of it. But for now, let's consider this one. As you can see in this, as this object is going to move down, what is going to happen is the body is going to get speeded up. So as it speeds up, uh, you can say its kinetic energy will increase, but at the cost of what? At the cost of gravitational potential energy. Why? Because with time, as its height is decreasing, the gravitational potential energy will decrease. So that's what we are saying. With time, kinetic energy graph will keep on increasing, and potential energy will keep on decreasing. Because if something is moving down, it's losing gravitational potential energy because it's losing the height. And it will gain kinetic energy because it's gaining the speed. So that's what we are saying. The sum should be equal. Kinetic energy itself is getting, sorry, gravitational potential energy is getting converted into kinetic energy as the object moves down. So that's what the basic idea is, which this law is trying to convey. In fact, we can very smartly use it in questions. In fact, the questions that we have already done in previous chapters using previous concepts, same thing can be done using our new understanding of conservation of energy. See, this question is pretty interesting. We have done this a number of times in previous chapters, kinematics, work energy theorem also we have solved this with. But now let's see the next way of doing it, which is conservation of energy. There is an object, it has been thrown up with speed u. We have been asked, okay, it's going to move up, will follow a projectile trajectory, but a vertical projectile, and will come to rest and will finally come down. We have been asked the value of maximum height attained. Actually, we already know it. We have done it so many times. We actually have the value in our mind. But let's try to derive it using conservation of energy. Mass is not given. Let's assume mass to be something. Let us assume it to be n. So we have been asked the maximum height, basically this point till where the body goes. That is what has been asked. So at the topmost point, body will come to rest now because it is at the topmost point. We know it's going to turn from there. Speed, or I can say final velocity, will be zero. So by the time the body's height increases from this point to this point, what is the energy which has been gained and what is the energy that has been lost? That is what needs to be thought about. We can say there is gain in gravitational potential energy because the height has increased. But at the cost of what? What is the energy that is being lost? That is kinetic energy. There has been loss in kinetic energy. Now, let's start one by one. What is the gain in gravitational potential energy? Gravitational potential energy's gains expression is mgh. In this case, the height through which it has increased is, like it has been raised, is h max. So mg into h max is the gain in gravitational potential energy, and it is coming at the loss of kinetic energy. How much is the loss? Now, guys, remember this: gain in is always final thing minus initial thing. That is what gain is, because in gain, final value is greater. For example, you have 2 rupees, now you have 8 rupees. What's your gain? 8 minus 2. But on the other hand, loss is initial minus final. For example, you have 8 rupees and now you have 2 rupees. What's your loss? It's 8 minus 2. It's initial value minus final value, because loss and gain both are by definitions always positive. If you're thinking loss is negative, no, that's change which is negative if something is reducing, but loss is always positive, gain is always positive. So loss we can say is final kinetic energy, initial kinetic energy minus final kinetic energy. That is half m u square minus half m v square. We know v is zero. Let's put it zero already. So mg h max is equal to half m u square, and h max equals to m will cancel m u square by 2g, which we already knew will be the answer. So this way we can use conservation of energy also to solve the same question. So that's the one of the simplest applications of conservation of energy. With this, let's move to the next question. Another question is, find the maximum length traveled by a block of mass m projected with speed v naught up the inclined plane, inclined at an angle theta with the ground. Let's draw the circle. Seems like a lengthy question as of now. So there is this inclined plane at an angle theta. There is a block of mass m projected with a speed v naught up the inclined plane. Yeah, I think we have done everything. Yeah, we have been asked what is the maximum height up to which maximum length traveled by the block before it comes to rest. So see, if we are asking the maximum length traveled by the block, basically what it means is the distance it travels before it comes to rest. But you can, because you can imagine after that it's going to come back. It won't be the length traveled along the inclined plane up in the direction of v naught. So after it comes to rest, it's going to revert back. So The maximum length is this when it comes to rest, right? We are supposed to find this. So, what will the equation of conservation of energy be? Think about this. Conservation of energy. Which energy is being lost and which energy is being gained? Body projected velocity v naught. It slows down, slows down, slows down, slows down, and at the top comes to rest. Which energy is lost and which energy is gained? Again, there is gain in gravitational potential energy at the loss in kinetic energy, at the cost of loss in kinetic energy. Right, you can imagine this. So, what is the gain in gravitational potential energy? Gravitational potential energy is gained as mgh. But in this case, okay, we'll discuss it. And loss in kinetic energy, initial minus final. Okay, now let's start thinking about h. What is the height through which the body has risen vertically upwards? Because if you remember, in gravitational potential energy, only the vertical distance matters, the vertical displacement matters. Vertically, how much has it moved? If you would say L, that's not correct. L is along this direction, but this is not vertical. What is the component of it along vertical direction? That is what is needed to be taken. And you can pretty much imagine it is actually this distance. This is the height through which it has risen. And using trigonometry, you can think this is L sine theta. So the gain in gravitational potential energy is mg into L sine theta. That's it. Because the height through which it has risen is L sine theta. I think this is pretty much understood. Loss in kinetic energy, initial half m v naught square minus final, 0, body comes to rest. So that means the length through which it rises is m gets cancelled, v naught square by 2g sine theta. And that is the answer. So what we understand from this is body can move in any direction. But if you're talking about gravitational potential energy, only consider the vertical displacement, not others. Okay. So with this, I think we can move to the next question also. A body of mass m is projected with speed v naught on a rough horizontal ground. Let's draw this. There is this horizontal ground. Body of mass m is projected with speed v naught. Okay. Using conservation of energy, find the distance traveled after which the speed becomes half. Okay. Why would it half? Because it's rough. The surface is rough. There is friction. So it's going to get decelerated. So we have been asked the distance, let's call it L, it travels before its speed becomes half. That is V naught by 2. Hmm. So we are supposed to use conservation of energy and let's try to see which energy is being lost, which energy is being gained. Think about this. Which energy is being lost and which one is being gained. Now you might be thinking, definitely the kinetic energy is lost. Earlier it was very fast V naught. Now it's traveling with half the speed, V naught by 2. So yes, it's true there is loss in kinetic energy. But at the cost of what? What is kinetic energy getting converted into? Gravitational potential energy. No, because the height of the body is not increasing. So basically it remains at the same level. That means gravitational potential energy is not increasing. It is this kinetic energy is not getting converted into gravitational potential energy. But somewhere this energy must be going. So where is it going? Now let's think about it. The only difference in this question and the previous questions was the friction. Friction is there. So if there is friction, uh, is any energy converted because of friction in some form? It is. For example, I start rubbing my hands. So suddenly the hands get heated up. Heat energy is generated. So that is the energy that friction converts, like that is the form in which friction converts other energies in. For example, in this case, kinetic friction. So kinetic energy will be converted into heat because of friction. Whenever there is friction, you can imagine, whenever there is kinetic friction, two things are slipping over each other, heat would be generated. So we can say there is loss in kinetic energy. Kinetic energy is being lost because it is getting converted into heat. So loss in kinetic energy is equal to the heat generated. That is what conservation, that is how the equation will hold true in this case. Conservation of energy is equal. Now the question is, how do I write how much heat is there? For kinetic energy, we have formula half mv square. For gravitational potential energy, mgh, positive, negative, depending upon gain or loss. But heat, yeah, let's see. Heat developed is always the magnitude of work done by kinetic friction. Like whatever amount of work kinetic friction does, the magnitude of it is called heat generated. Let's see. In this case, how much is the work friction did? Kinetic friction did. First, let's write the expression for kinetic energy, kinetic friction. So kinetic friction we know is coefficient of kinetic friction multiplied by normal reaction. Normal reaction in this case, mg, because vertical it's not moving, mg downwards, normal reaction. So yeah, kinetic friction in this case is mu k mg. But direction you can imagine is leftwards to oppose the motion. So Fk kinetic friction is acting leftwards. But what is the displacement? Rightwards L. So this means definitely friction must be doing negative work. Work done by friction is minus Fk into L, because Fk into L into cos 180 of the direction. So yeah, negative work it's trying to slow this down. Agreed. So that comes out to be minus mu k mgl. That is the work done by friction. But as I said, heat generated is magnitude of the work done by friction. So let's start from the left hand side first. The work done by the loss in kinetic energy is initial kinetic energy minus final kinetic energy, and the heat generated is the magnitude of work done by friction. So loss in kinetic energy, let's write again, that is going to be half m v naught square minus half m v naught by 2 square, initial minus final. And that goes into the heat developed. That is the work done by friction's magnitude. That's mu k mgl. So this finally gives us that the length over which, like the distance traveled after which it comes to stop, is 3 by 8 v naught square by mu kg. Yep, that's correct. Hmm. So that is how you can actually find the distance traveled by work done by friction also. Basically, frictions also converts one energy, that is like converts energies into one form of energy, that is heat. So this is what we learned from this. So that is it. I hope that is very much clear. In the next lesson also, we're going to discuss things related to some other form of potential energy that is going to be interesting. We'll be solving questions using these concepts and that new concept also. So let's see what we discuss. It's going to be interesting. And if you have any doubts, please post on the bash discussion forum. And all the best.